My name is Jitter and I will moderate this webinar today. Our topic of today is how to debug signal integrity with power integrity. Our speaker today is Suhonen Pasi. Suhonen, welcome. He's from Rode and Schwarz. Very cool to have you here. Signal and power integrity go hand in hand, but how do jitter and eye diagrams reveal system behavior? Let's connect the dots. Stage is yours, Suhonen. Have fun.
Hello, and welcome to this webinar on how to debug signal integrity with power integrity. My name is Pasi Suhonen. I'm an application engineer for oscilloscopes at Rode and Schwarz. In this session, we will be looking for the fundamentals of the signal and power integrity and how an oscilloscope can be used for debugging these issues. Let's start with some definitions. Signal and power integrity and EMC problems can be grouped into the three different categories. Signal integrity describes the ability of the system to transmit and receive data signals properly. This means basically how electrical properties of the interconnects that are interacting with the signal's voltage and current waveform affects the performance itself. Power integrity groups several measurements to qualify the quality of the power supply and distribution network. EMC means a contribution to radiated emissions or susceptibility to electromagnetic interference from external fields. So, what type of measurements are typically done for signal and power integrity with an oscilloscope? For signal integrity, we typically measure eye diagram, jitter, noise, crosstalk, and timing-related issues. For power integrity, voltage level and offset, AC ripple and harmonics, groups and distortions, and long-term stability issues are measured there. So what does power integrity mean? Power integrity is the analysis of DC power rail to determine the quality of the DC power from output to the DC converter to the ICs, for example. Typical measurements such as ripple, noise, and load response measurements on integrated circuits like CPUs, DDR memories, and FPGAs require very low noise broadband probing solution that can be measured in a single-digit millivolt range. Qualifying the power supply for sensitive analog receiver circuits means measuring very small disturbances at relatively high DC offset levels. Design of modern equipment can include tens of power rails managed by complex power distribution networks. PDN is including complete system, not just DC to DC converters and internal chip to power distribution, but also every interconnect, trace, via, connectors, capacitors, packages, pins, and ball grids. Then, what are the typical challenges for power rail measurement? For example, lower rail voltages and smaller tolerances are making it more difficult to make accurate power rail measurements. As rail voltages get smaller, so has the tolerance associated with these rails. Even older standards like 5V and 3.3V rails may now have tighter tolerances than a few years back. So measuring 10% tolerance on 5V is 500 millivolt and thus simple to do on any scope. But measuring 1% tolerance on 1V signal is 10 millivolt and therefore very difficult to do with most scopes, as the scope's internal noise impacts the measurement itself. Differentiation in time domain become a tough task for signals that are smaller than the noise of your oscilloscope and probing system. When a signal enters to the oscilloscope front ends, then the noise gets added to the signal before the analog to digital converter. Each stored sample now includes the value of the original signal, but with some offset based how much noise was present when the sample was acquired. Let's say we need to measure low-level signals, but due to the noise added to the measurement system, including scope plus probe, peak-to-peak voltage greater than what are the true signal values are shown and measured. The best approach is to start with oscilloscope that has low intrinsic noise level and select proper probing system for this kind of measurements. Let's take a look at the probes that are typically used in power rail measurements. First probe type is single-ended 10:1 passive probe. Some of the advantages these probes are: it's 500 MHz bandwidth with 10:1 attenuation, good dynamic range, and it is low cost. So what are the disadvantages? First of all, 10:1 attenuation adds noise to our measurement, and thus it can be seen in the measurement itself because there we are overstating voltage when comparing it to proper measurement value. By having huge offset needs, you may not be able to adjust the offset with the offset compensation range of the oscilloscope itself. Therefore, your measurement error will increase dramatically because most of the ADC resolution will be used to characterize DC offset, and less ADC bits are left for characterization for your actual noise signal itself. By adding AC coupling, you are not able to characterize DC drift, which is very important parameter regarding power rail measurements. Second probe type is 1:1 passive probe. Advantages for these probes are 1:1 attenuation, good dynamic range with low noise, and it is very low cost probe. 1:1 probes has limited bandwidth. In this case, RTZP 1X probe has only 38 MHz of bandwidth. Due to a limited probe bandwidth, higher frequency components will be cut off, and therefore you get underreported voltage measurement values. Here you also have offset compensation issue, and therefore measurement results are overstated. And also, by adding AC coupling, characterizing DC drift is not possible anymore. So, considering pros and cons for previously presented probing solution, a dedicated power rail probe has been designed. Rohde & Schwarz offers two different types of power rail probes. In practice, they differ only in bandwidth. Main advantage for dedicated power rail probes are following. Probe has 1:1 attenuation and high bandwidth, therefore noise will be minimized and high frequency peaks from the signal can be seen. DC offset compensation range for power rail probe is huge, meaning we are able to use full ADC range for AC component characterization. And finally, we are able to measure DC drift and therefore see how large DC variations will be in your circuitry. Let's take a closer look at some primary specs of our RTZPR power rail probes. The characteristics mentioned here in blue line up with so-called top concerns of the power rail measurement. First of all, probe has 1:1 attenuation, and thus it's adding less noise into your measurement. 2 or 4 GHz bandwidth enable capturing high frequency transients, which might result from cross-coupling, for example, wireless LAN system. DC offset range for this probe goes up to ±60 volts, which is best in its class. Probe has very low intrinsic noise level. This means we are increasing RMS noise level of our measurement system only by 13 microvolt when using this probe. And last but not least, probe has 50 kilo ohm input resistance, thus loading effects at the lower frequencies is significantly reduced. So, jumping to a signal integrity. Typical debugging session for signal integrity starts with so-called eye diagram measurement. If we think about transmitter, an eye diagram typically looks open and clean at the output of the TX chip. When signal travel via PCB trace to receiver board connection, some dispersion effects like attenuation and phase shift will occur, and therefore eye gets more closed at this point. Next, signal is traveling from receiver board connector to RX chip input, and for example, in this case, high-speed serial bus eye will be distorted at this point. Therefore, so-called equalizer is used in high-speed serial buses, which is able to recover closed eye, meaning bit errors will be significantly reduced at the receiver side. Common signal integrity issues include problems such as ringing, overshoot, undershoot. Signal attenuation in PCB traces and cables, for example. Crosstalk in adjacent lanes due to the unwanted cross-coupling. Reflections due to the impedance mismatches in transmission line itself. EMI interference coming from system itself or from outside of the system. And of course, noise caused by power distribution networks. So how are signal integrity and power integrity linked together? When thinking about power rail noise, we are having instrument noise added to it. And thus we are seeing this combined signal in the oscilloscope screen. For example, NRZ-coded signals have certain high, low, and threshold levels, and between those levels we have a rising and falling edge of the signal. If then, for example, we have some reference voltage which is varying due to the noise issues, threshold level will also be varying up and down a little bit. This will cause shift in time of the signal edge itself, because signal will be entering more early or too late to the threshold level. This means added noise will cause noise to jitter conversion, and this will add up so-called jitter itself, because it's closing the eye at the end. So what is an eye diagram and where do we need it? An eye diagram is a graphical tool for evaluation of the quality and integrity of the data signals. It is generated by superpositioning short segments of waveform in a way that the nominal edge locations and voltage levels are aligned, resulting to a shape which is similar to an eye. Eye diagrams are usually drawn either in monochrome or color trace to indicate the density of the waveform samples at any given point of the display. So how do we generate an eye diagram? For that we need to have a reference clock which triggers the oscilloscope into the input data stream, as shown in here. Measured waveform is sampled synchronous with the bit rate of the signal and randomly over time. In this process, input data stream gets sliced. An eye diagram is generated by superpositioning of multiple input data streams waveform segments, which are aligned to well-defined reference clock instance. By overlaying rising and falling edges of the signal, an eye diagram gets built, and from there it is easy to visualize the signal behavior. Eye diagram provides a lot of statistical information about the signal quality. Typical eye diagram looks like this in an oscilloscope screen. First of all, eye should be kept as open as possible in order to get a good signal quality. Usually, mask test is used for quickly verifying signal quality. Mask defines key areas in the center of the eye that are to be kept clean. If any of the signals is detected inside the mask, then the test is failing. Jitter can be directly measured by investigating eye diagram crossing points. Noise level of the signal can be investigated from top and bottom part of the eye diagram. And if you have high noise level in your signal, noise to jitter conversion can be observed by increased jitter at the eye diagram crossing points as shown here. Typical measurements such as eye height and eye width are performed in order to determine that the open part of the eye is with acceptable limits. For proper eye diagram generation, we need reference clock signals, which is somehow synchronized to the data signal itself. Here you can see basic block diagram for typical high-speed serial link, such as PCI Express or USB, for example. At the transmitter side, we serialize parallel input data and then add bit clock into it. Timing reference, meaning the bit clock can be separate reference signal or embedded into the serial data stream itself at the transmitter side. At the receiver side, the fundamental block for recovering reference clock is clock data recovery circuit, consisting typically of phase locked loop or delay locked loop. The PLL receives a reference clock signal at its input and uses the phase detector to measure phase error between reference signals and voltage controlled oscillator, so-called VCO. The phase error is filtered through the loop filter and applied to the control voltage of the VCO. The loop filter prevents fast changes in the phase error from being fed back to the VCO, and as a result, VCO is adjusted only on slower changes in the phase error itself. In this way, PLL acts like a flywheel in that the average frequency of the VCO is steady even when there are rapid changes in the phase of the reference signal itself. There are typical approaches for generating an eye diagram. First one is so-called software-based post-processing. For example, USB 3.2 Generation 1 standard requires that you need to acquire long bit sequence, and in this case, 1 million bits for generating an eye diagram. This means oscilloscope need to make long signal acquisition leading to a long record length. Software CDR algorithm is used to recovering reference clock, slicing input data stream bits, folding waveform over into the eye diagram, and showing it in the oscilloscope screen. One downside for the approach is that software CDR settling time is long, and it needs new synchronization for every new acquisition. In general, software-based post-processing leads to a long blind time between new acquisitions. This means in practice, for example, oscilloscope waveform update rate is reduced, meaning we need to measure longer time in order to get good set of statistical information for our eye diagram measurement itself. Main application for this approach is investigating long-term stability of transmitted signal. Second approach is so-called real-time eye diagram based on hardware CDR. In this architecture, signal is fed from DUT to the oscilloscope vertical input amplifier and from there to the AD converter to be digitized. Then all digital samples are fed into the memory. Our RTP oscilloscope has unique digital trigger system including hardware clock data recovery to bit slice a serial data stream with embedded clock. This block is placed between AD converter and memory. Main advantage for this hardware CDR is that it continuously follows the drift of the input signal in real time, unlike post-processing software CDR requires longer PLL settling time per waveform acquisition. Digital trigger and hardware CDR makes it possible to acquire a lot of short-time acquisitions from input data stream instead of one long single-shot acquisition. With this approach, waveform update rate for our RTP oscilloscope can go up to 400,000 UIs per second while measuring eye diagram. This gives us many benefits, such as gathering a lot of statistical data for eye diagram measurement in short measurement time and searching for short-term events that might corrupt the eye. Also, eye diagram is updating in real time on the oscilloscope screen, meaning it can be instantly shown any changes in the incoming signal itself. What are typical causes for jitter and how can jitter separation help you for debugging your circuits? So here you can see that the total jitter is divided in random and deterministic part. So in random part, the typical sources for random jitter are thermal noise, shot noise, external radiation sources, and oscillator instabilities. So all these effects are theoretically unbounded in the frequency range. For deterministic jitter, it is again divided in different components such as transmission losses, circuit bandwidth, frequency-dependent losses, dielectric absorption, dispersion and reflections, and impedance mismatches. So all these are material parameter effects, to summarize them a little bit more together. And also here, the spectral components of the deterministic jitter part are bounded and always rely, for example, for the data rate itself. Next is duty cycle distortion, meaning rise and fall times, mismatch, as well as offset errors. For periodic jitter, we could have, for example, injected noise, circuit instabilities, switch mode and oscillators plus harmonic contents which are going around in your system, also PLL stability problems, and loop bandwidth tracking and overshoot issues. For a bounded uncorrelated jitter, major source today will be crosstalk from adjacent lanes. So here, if you, for example, think about PCI Express lane, there we typically have more than one lane, and for the current interfaces, we go up to 16 lanes in parallel. So in this case, the neighboring lanes could have cross-coupling, so these effects can also be quantified as a deterministic jitter. So here, if you think about frequency domain, it is bounded jitter term, but it's uncorrelated to the data source itself. And that is why we are talking about bounded uncorrelated jitter in this case. This means that frequency range is limited and it is not depending on the signal itself we are trying to analyze. And of course, jitter because it's a variation in time. Our jitter decomposition algorithm is based on parametric signal model that fully characterizes the behavior of the transmission path under test. The main advantage of this method is that it is utilizing the complete waveform characteristics, including the vertical and horizontal components. This leads to more accurate and more consistent measurement results, even for relatively short signal sequences. The core element of the signal model is step response that describes the data-dependent characteristics of the signal. The model also includes the periodic and random jitter terms. So here, as a first step, we are acquiring a signal out of the DUT, and from there it is routed to the clock recovery circuit. Then we are doing bit decoding. So we are measuring the actual signal to be reconstructed later on. After the clock recovery and bit decoder, we can measure total time interval error, meaning we have an ideal clock and actual signal, and therefore we could directly measure the differences between these two signals. With single model-based approach, all non-idealities of the measured signal lead to a channel estimation, and thus step response can be given, which includes several useful information like overshoot and ringing, and as well impedance mismatches and ISI behavior. In this block, we are also computing periodic, vertical, as well as horizontal components because we are doing an analysis on complete signal. During the decomposition process, a least square estimator compares the input signal to the signal model and calculates the parameters of the signal model. Then, based on the input signal's bit sequence, the algorithm reconstructs synthetic signal sequences for individual deterministic jitter components. Afterwards, we could do the split in the data-dependent and periodic vertical components, and finally display measurement results in the oscilloscope screen. As data rates and slew rates increase, the resulting bandwidth increases, and thus also resulting noise in the DUT. Therefore, separation in pure timing and noise effects become more important nowadays than it has been in the past. Here we are splitting total noise inside the signal also into the random and deterministic components. So our jitter algorithm gives you possibility to select random plus other bounded uncorrelated noise components to be shown separately or together. Algorithm also provides the decomposition of the commonly known noise components such as data-dependent, periodic, and intersimple interference noise components, just to name a few. So our advanced jitter algorithm application is providing a lot of valuable information for circuit debugging purposes. First of all, smart grid functionality of the user interface can help you to arrange the scope screen in the best way, so that you can only view those measurement results that are for interest to you. Algorithm is also capable for providing new insights to measurement results, such as synthetic eye, which is calculated from reconstructed signals. Step response allow you to get direct estimation for the quality of the transmission channel itself. Periodic jitter components are arranged into the table showing frequency and value and direction, horizontal indicating timing error and vertical meaning amplitude error. Here especially the extrinsic and intrinsic statement is unique, as you get some guidance which components will most likely be coming out of your signal itself and which are caused by external interferers like switch mode power supplies, oscillators or other components. We could also have different views on the bathtub curve, including total jitter or alternatively data-dependent plus random jitter without periodic jitter components. For long-term statistical and accurate eye diagram measurement, we need to have some real-time capabilities inside our instrument. So this slide gives you an overview of our RTP oscilloscope real-time de-embedding architecture. So here, if you look at this picture, we have device under test and we have a signal traveling from this lossy signal path into the input of the oscilloscope itself. And due to this lossy signal path, the signal will be distorted at the input of the oscilloscope. So this could be compensated by using so-called real-time de-embedding, and therefore we are able to open up the eye again. So with this embedding, we are compensating basically the lossy channel, opening up the eye and getting the real signal values at the test point of the DUT. After the de-embedding, there is real-time math module enabling RTP oscilloscope, for example, to display differential and common mode signals together. Then this oscilloscope has a digital trigger architecture, which is capable to trigger on de-embedded differential signal and then analyze the signal further on. Here it is very important to notice that the trigger types are operating always on full bandwidth and the full screen of the oscilloscope, because we are operating after the ADC. And finally, our oscilloscope has also integrated hardware-accelerated analysis features for mass testing and histograms in the acquisition board itself. And then the final step is to display fast updated waveform at the oscilloscope screen. So with this architecture, we can reach up to 400,000 UIs per second. So how to check for signal integrity issues? Real-time eye approach utilizes hardware CDR as a trigger source and captures up to 400,000 UIs per second. This gives us benefits such as searching for short-term events that might corrupt the eye. A lot of statistical data can be analyzed in the short measurement time from waveforms by using histograms, for example. Software CDR approach uses longer acquisition time, thus long-term stability of the signal is investigated. Software CDR algorithm is used to slice acquired data and display the eye diagram. And then finally, if the eye diagram does not give any sufficient details, jitter separation can be activated on the same acquired signal. With jitter separation, you are able to unreveal the sources of the signal distortions by displaying selected jitter terms in the oscilloscope screen. So that was the end of the theoretical part, and now it is time for demo with the real instrument. So here I'm showing the demo setup, what we have arranged here. What you can see here, we have a device under test, which is basically USB 3.2 generation 1 memory stick. Memory stick is connected to the test fixture, and then we are able to measure the TX line of the USB stick itself. Connection between the oscilloscope and the test fixture is differential. So from TX plus line, we are connecting one cable to the oscilloscope channel 1, and from TX minus line, we are connecting one channel to the oscilloscope channel 3. So jumping to our scope screen, first thing we need to do here is to activate differential measurement, and we need to activate channel 3 also. So let's activate these two channels. So channel 1 and 3 are activated, and then I shall couple them together in order to control the amplitude for both channels in one place. This is now done. Then we need to activate our hardware differential module. And from that one, as an input signal, we have positive and negative. Positive is from channel 1, negative from channel 3, and as an output, we have differential and common mode signals. Then we will enable that. This is now done. Then common mode can be minimized. Next, we need to adjust our trigger into the differential signal. So trigger source here will be differential. And after that, if we want to measure eye diagram, we need to activate clock data recovery. So I go for the CDR. Then under the tab hardware CDR, I need to give parameters for clock data recovery circuit. And as a serial standard, I can select USB 3.2 generation 1 and estimate bitrate. And there we have now stable eye diagram measurement going on. So maybe we can scale up the horizontal scale a little bit so that we can see 1.5, maybe 2 eyes here. Next, we can measure this signal. So for example, with the simple mask, I will press this mask button and then draw mask here into the screen. And maybe we can do some automated measurements directly also from the eye diagram itself. So we go to the measure menu, advanced setup, then our source shall be differential, category will be eye, and from here I can add different measurements for the eye diagram. So just for example, I take eye height and eye width and go back in there, and now these measurements are also activated in here. So what we can see here, we are running a mask test. Mask is the gray area in the center of the eye. And here we can see the mask results in this small window. And the automated measurement functions, which are running also in the background, is this eye height and eye width. And the current value for that one is shown in here in these columns. So I am also injecting an external interferer from our arbitrary waveform generator into this power rail of the this demo board. So let's see if we can pick up that interferer with our jitter solution. So let's press preset. Then we need to activate 2 channels again, couple them together. And from here, I'm able to control both of these channels simultaneously. 60 millivolt per division is a good value for that. Then activate differential, minimize common mode. Then the trigger source shall also be differential in this case. And for the jitter measurement, we might give it a little bit more memory depth. So something like 400 kilopoints could be a good starting value for that one. Then let's activate the algorithm itself, advanced jitter and noise. Here, as a first step, we need to activate what is our analyzed signal source. And in this case, it's going to be differential. And we are measuring jitter from data signal. So this data NRZ is a correct value for that selection point there. Next, we need to determine our CDR settings for the jitter measurement. Here I can also set USB 3.2 generation 1, estimate the bitrate, and then I need to select what jitter components I want to see in my screen. So here, tab called jitter, I can add and remove components. Everything you see blue here are selected. So in this particular measurement, I shall select random jitter plus other bounded uncorrelated jitter, total jitter, and periodic jitter and deterministic jitter values. These are now selected. Then I want to see histogram for every single selected components, and after that I can enable the algorithm itself. Next, we are going to look at more detail these histograms. So I will arrange these also into the small windows into the screen. So let's put total jitter here, deterministic jitter on the right-hand side, periodic there, and there we have all our histograms. So what we can see here in the top right corner, we have the jitter analysis results for total jitter, deterministic jitter, periodic jitter, plus the random and other bounded uncorrelated jitter. They are all arranged into this table here. And also what is interesting to see here is these periodic components. So here, for example, we can see frequency, value, and direction. And in position number 9, we can see 10 megahertz interference signal, which is in fact coming from the arbitrary waveform generator of the oscilloscope. So we can see the frequency of that one, and we can see the voltage value for that one, and we can see the direction, meaning vertical, meaning the noise. Also, in the histogram itself for the periodic jitter, which is this orange one, we can see that it's sort of a bimodal looking. So it's an indication also that there is a strong periodic component present in our circuit. Next, I can switch off the generator and see how the results will look over there and disable it. And now we can see 10 megahertz is basically gone from these periodic components. So that was all for this short demonstration. Thank you for joining this webinar, and I hope you enjoyed it.
Yeah, thank you, Suhonen, for your interesting presentation. Now we will come to your questions. Before we start with the live Q&A, I will share the handout from the presentation from Suhonen. So now everybody can download it, the handout. Suhonen, can you hear me?
Yes, I can hear you.
Perfect. Cool. Are you ready for the questions?
Yes.
Good.
Start.
Then we can start with the first question. Power rail probe is very expensive. Would it be possible to just solder coaxial cable directly to power rail and measure low-level ripple without the probe?
Yeah, here I would say that it is possible up to the certain voltage range, and the things to be consider here is that first of all, when you connect direct coax connection to your oscilloscope, you get full analog bandwidth of the oscilloscope in your use. So whatever analog bandwidth you have in your scope, that's your measurement bandwidth basically. Then you get one-to-one attenuation, and that means that intrinsic noise level of the oscilloscope is varying depending on the vertical settings. So usually we are measuring quite low level of ripple signals. In this arrangement, you can adjust your vertical scale to quite sensitive level and therefore reducing your intrinsic noise level also. So you have a high bandwidth, you have a really sensitive measurement, you can measure small signal levels, small ripples. But the downside here is that you need to be aware of the oscilloscope channel voltage offset, and that also is changing according to the vertical scaling. So you, at some point, you might run out of your offset settings on your channel, and there you cannot really measure anymore when you have a high DC voltage level. Of course, you can use this DC block capacitor for that one, but like in the presentation, I mentioned that it will block the information about the DC. And usually in the DC voltage rails, we want to see what's the real DC value. And so there are pros and cons. So the answer is you can do it, but with certain limitations.
Thank you. Then jump direct in the next question. So time is running.
Yes.
This one. I did not quite catch why jitter separation is really needed for high-speed digital signal measurements.
Yeah, that's a good question. So we see that there's two parts of that. First of all, when you do some compliance measurement for your devices, usually in the standards, they are defining some certain jitter values for certain jitter components. So they are stipulated in the standards itself. So that's the first part. Compliance testing, there you need to have this information. And then the second one is maybe also really important aspect. So if you fail on your compliance, then you typically go for debug mode and you start to debugging your system. And our jitter algorithm gives you really cool debugging tools. And the main aim for those tools are to identify the root cause of your jitter so you can fix the hardware in able to get clean signal again. So compliance and debugging, those are the main two aspects for this jitter separation.
Thank you. Then next question from Sia Wash. Is MIP, I would say, communication include into your oscilloscope serial standard?
Here the answer is yes. So we support compliance testing for MIPI, we support trigger decode for MIPI, and also debugging mode. So debugging means you can generally measure the electrical characteristics of the MIPI signal, also measure the eye diagrams and all those. So MIPI is definitely supported in our RTO and RTP oscilloscope series.
Okay, thank you. Then I would say one last question. The second question from Sia Wash. How to interpret the jitter result value? Is there any standard to see if fail or acceptable?
Yeah, that's a good question. Typically, you have inside the standards, let's take, for example, USB. So they are stipulating inside the standard what are the typical jitter values for certain components. So that comes to the compliance testing. Of course, you can have your in-house limits, what you can do, and also some chip vendors, they are defining some jitter values for their chips. So on the data sheets and in the standards, you can find this information related to jitter values itself.
Thank you. Then I would say we are finished with the session. Thank you, Suhonen, for your time, for the answers, and for the very interesting presentation. Yeah, I will share the link to all the other sessions during this week at the Digital WE Days. So with Jitter now, and hopefully you see us on our next session. Thank you for your attention. Thank you for your interesting, and yeah, have a good day and bye-bye.